This is section 5.5, the substitution method, the third and final objective, which is to evaluate definite integrals using the substitution method. If you watched objective 2, where we evaluated indefinite integrals, you'll realize that there are distinct similarities between the steps for both. When we're done, I'd like you to discuss how these steps would change if you prefer to substitute x back into your antiderivative before evaluating. So let's just read through these steps really fast. Number 1 is the same, number 2 is the same, number 3 is the same. What's different is that we are now going to change our limits to u limits. And when we do that, we'll create that constant multiple of an easy and definite integral, just like we did before. And then when we evaluate, we will not have to go back to x's because we can just evaluate using the new u limits. So we'll see this in action with our examples. With example 1, we are looking for an inner function whose derivative is also inside the integral. So we could put a box around the 5x cubed because if I take the derivative of something with an x cubed, I'm going to create an x squared. So what we'll want to do with the substitution method now is we'll want to replace both the u and the dx, and we will replace the dx by finding du dx and then isolating dx. When I substitute now, everything will stay the same that is not in a box, and everything that is in a box gets replaced with u or something involving u. If we've done this properly, then things that do not have x's in them will disappear, and things that have u's in them remain inside, and the coefficients can go out. Now our next step is we've got to address the limits. These limits were limits on x. So our goal is to figure out what u is going to be when x is 0 or when x is 1. So we find them by finding our lower and upper, by taking our u and then plugging in our lower and upper x's. So this would be 5 times my 0 cubed, which is 0. And my upper limit will be 5 times my 1 cubed, which is 5. So my new limits, when I change to u's, will need to go from 0 to 5. On the AP exam, they will often test whether you know the substitution method simply by having you convert something that's in terms of x's to something that is in terms of u, and so they'll force you to find those u limits as well. So now that we're here, we've created a problem we should be able to go backwards on. So we will move through the constant and answer the question, what did I take the derivative of with respect to u that gave me u to the 4th? Well, that's u to the 5th over 5, and I can evaluate from 0 to 5. That will give me 1 over 15 times 5 to the 5th over 5 minus 0 to the 5th over 5. If I simplify that, I get one of the 5's will cancel, then another one of the 5's will cancel, have 5 cubed, which is 125 over 3 minus, this simplifies to just a 0. So I end up with 125 over 3. With example 2 now, we can look for an outer function that we know how to go backwards on, in addition to an inner function whose derivative is also in the integrand. I know how to go backwards on secant tangent because that's on my green sheet. So what's inside the secant tangent is what I'm going to check to see if it makes a good choice for a u. If I take the derivative of that, I'm going to get something involving a w raised to the power of 1. So if I isolate dw, I'll have du over 4w, and that w is going to cancel this one, so I know I've made a good choice. If I am to replace everything that's in a green box with things involving u and leave everything else the same, then we see that we'll have a u here, and a du over 4w. The w's, which were the original letters, will vanish, and everything left inside will involve only u's. So I can pull that constant out in front and have the secant of u times the tangent of u with respect to u. If I want to now examine the limits, we can see that our lower u is going to be 2 times our lower w squared. And that gives us 2 times a pi over 8 or a pi over 4. So my lower u limit is pi over 4. If I look now at my upper u limit, we see that we get the exact same thing. You'll notice that this process simplifies the integration very quickly because my upper and lower limits are the same. I know that that answer is 0. With example 3 now, we're looking for an inner function whose derivative is also inside. So I'm looking first at what seems most complicated that's inside something else. So I'm going to try and work with this 3 minus w to the 3 halves. And we'll just try that and see if it works. If this is a good choice for u, then when I take the derivative of it, I should get a multiple of what else is inside here. So move through the 3, move through the negative, bring down the power, and reduce that exponent by 1. Notice that this is negative 3 halves times a square root of w, and there's that square root of w. So I probably have made a good selection, which means I'm now going to isolate my dw because I want to replace both the u and the dw, and that would give me a du divided by a negative 3 halves root w, which is really just a negative 2/3 times the du over a root w. If I now do my substitution, everything that is not in a green box is going to stay the same. So I'll have a 12 root w over something cubed, and then I'll replace the boxes with what they equal. When I do this, I can see that the w's will disappear, and I will have a constant coefficient that I can pull out. So I'll end up with a negative 8 times the integral of, rewrite this as a power rule, and I'll get u to the negative 3 with respect to u. I'm ready to go backwards now, but before I do that, I want to examine and make sure that I change my limits. So I will have a lower u limit, and I will have an upper u limit. The lower u limit will come from plugging the 0 into my u. Well, that gives me a 3. My upper u limit comes from plugging my upper w limit in for my into u, and that'll give me a 3 minus 1, which is a 2. So I'm going to actually be starting at 3 and then backtracking to 2. So I can rewrite this in the order I'm accustomed to working by doing the positive 8 with those limits switched. Now I'm ready to do the antiderivative, so I answer the question, what did I take the derivative of with respect to u that gave me u to the negative 3? Well, that says I'm going to add 1 to the exponent, divide by the new exponent, and then evaluate from 2 to 3. So that will be a negative 4 times a 3 to the negative 2 minus a 2 to the negative 2. Get a common denominator, or distribute, we'll have a negative 4/9 plus a 1. That looks like we're going to end up with 5/9. With our fourth and final example for the section, you might be feeling a little cocky because the ones that have come before this haven't been too challenging, so you might at first glance try to let u equal an x squared plus 16. But if you go through the process and you let du dx equal 2x, and then you isolate your dx, you will end up getting something that has an x on the bottom. And if we replace, there's no x up here to cancel out. So this is not a good choice. We cannot use that as our u. We have to backtrack and think about what else this might be the derivative of. If you go back and look at your green sheet, you should see an integral whose insides somewhat resemble this. And the one that I want you to find is the one that looks like this. According to our green sheet, this inside is the derivative of the tangent inverse of u. So if we can get this one to look like this one, we might be able to do the antiderivative. So let's look at how these compare. This one has a plus 1 and this one has a plus 16. So what we want to do is we want to create a plus 1. To get that plus 1, I'm going to factor out a 16. When I do that, I'll have an x squared over 16 plus a 1 inside those parentheses, because if I distribute the 16, I'll end up right back where I started. By doing that, I've now created an integral that has a constant coefficient out in front and a 1 over something squared plus 1. So let's figure out what that something is that got squared to give me an x squared over 16. Hopefully you can see that it is an x over 4. Now that we have converted how this one looks so that it's easier to recognize the parent derivative that's sitting in there, we can choose our u and our dx. So we can let u equal x over 4, which means du dx will be 1/4, which means if I isolate dx, I will get 4 du. So if I come back up here and replace, anything that is not in a box will stay the same. Anything that is in a box gets replaced with things involving u. Notice that anything that has x's has disappeared, and I can reduce and pull out that constant in front. So now I'll have a 1/4 times the integral of 1 over u squared plus 1 with respect to u. So I'm ready to integrate and find that antiderivative using my green sheet, but I need to make sure that I change my limits. So my lower u is 0 plugged into my u, which is 0, and my upper u is 4 plugged into my u, which would give me a 1. So I will integrate from 0 to 1. I'm now ready to answer the question. What did I take the derivative of with respect to u that gave me this inside? Well, that's the tangent inverse of u, evaluated from u equals 0 to u equals 1. Plug in 1, and we're going to answer the question, what did I take the tangent of that gave me 1? And then I'm going to subtract the angle whose tangent gave me a 0. If I answer that, I'll get a 1/4 times the angle whose tangent gave me 1 was pi over 4, and the angle whose tangent is 0 gave me a 0. So I'm left with a pi over a 16. So now what I'd like you to do is think about how these steps would have changed if we did not change our u limits. If we stuck with the x limits, what else would we have had to have done in order to arrive at the same answer?